We've all heard the industry assumption: if you want a fast system, you have to burn power. The prevailing wisdom dictates that performance and sustainability are natural enemies. That assumption is incorrect. We will dismantle that myth and look at the actual data. In most architectural scenarios, reducing the computational footprint drives both speed and lower emissions simultaneously. Our objective today is to equip you with the mathematical and logical frameworks required to make defensible, data-driven sustainability decisions about the systems you design. We will start by mastering the 5 dimensions of sustainable IT, then build a multi-criteria decision matrix, separate real tensions from illusory ones, apply concepts to a streaming case, and clear up the most common traps you will face on the exam. Carbon optimization serves as a rigorous test of system architecture. Let's get into the mechanics. This diagram outlines how 5 dimensions determine a system's environmental footprint. Infrastructure efficiency tracks hardware utilization. Software efficiency measures computation per result. Carbon-aware operation times workloads for clean energy. Measurement tracks consumption, and architectural choices ensure the system's shape matches its workload. The critical principle of this framework is that these dimensions are non-compensatory. A surplus in one area does not cancel out a deficit in another. Deploying a system on a grid running on 100% renewable energy does not mathematically excuse executing highly inefficient, wasteful code. This brings us to a specific exam trap. If you optimize language choice, data structures, or algorithms, you are improving software efficiency. It is a mistake to label this carbon-aware operation, which deals strictly with the timing and location of the workload. True architectural sustainability requires a holistic evaluation across all 5 levers. Optimizing a single metric will inevitably create blind spots elsewhere in the system. When sustainability competes with latency, cost, and compliance, we use multi-criteria decision analysis. First, non-negotiable constraints like data laws eliminate invalid choices immediately. For the remaining options, we assign percentage weights, score candidates, multiply, and sum the results to find a mathematical winner. Pay close attention here, because this is the focus of exam trap question 9. The absolute golden rule of MCDA is that criteria weights must be agreed upon and locked before any candidate options are scored. The primary failure mode happens when stakeholders see the final scores and start arguing to adjust the weights, attempting to favor an architectural choice they already preferred. Retrofitting weights actively destroys the framework's validity. It turns a scientific evaluation into an exercise in political justification. We must address illusory tensions, the false assumption that faster systems cost more energy. In reality, optimized algorithms, compact data, and right-sized infrastructure do less work, making them faster and cheaper. Real tensions only occur when architectures demand energy waste to guarantee safety or responsiveness. Idle capacity consumes power doing nothing. Cross-region redundancy duplicates data storage. Perfect cache freshness requires constant invalidation. When a tension is real, the architect must strictly prioritize based on the workload's specific lifecycle. A user-facing checkout flow needs low latency, while a nightly batch pipeline prioritizes minimal energy over immediate response. Correctly identifying what is an illusory tension prevents your team from rejecting critical efficiency upgrades based on an imagined performance hit. Let's apply this. A regional video streaming service with 1 million daily users committed to a 30% emissions reduction. One proposed engineering intervention is right-sizing the recommendation engine, stepping away from an architecture that is currently provisioned for peak load 24 hours a day. Does this right-sizing represent a real or an illusory trade-off against system performance? The trade-off is only real if the newly downsized engine fails to absorb sudden, unpredictable traffic spikes, causing latency for the end user. However, if the traffic scales predictably, the tension is entirely illusory. Right-sizing is actually faster because requests don't queue up, saving massive amounts of idle energy. Theoretical tensions must be tested against the actual behavior of the specific workload. That is the only way to determine if a trade-off is real. This chart shows the green software maturity progression, mapping how organizations adopt these practices over time. Let's look at how this appears on the exam. Question 5 targets the crucial difference between the awareness stage and the measurement stage. If a scenario states that rough, incomplete energy numbers exist, the organization has officially reached measurement. They are no longer just in the awareness phase. The quality of the data matters less than the fact that a baseline now exists. Finally, let's look at exam trap question 14, which deals with organizational failure modes. A common mistake is assigning the entire problem to a single central sustainability team. A central team can produce excellent reports, but they cannot dictate daily library choices, region selections, or caching strategies for individual product teams. They simply don't have the context. Sustainability ownership belongs embedded within the daily engineering teams. It must be integrated into standard code and architecture reviews, alongside performance and cost. System sustainability depends on thousands of daily micro-decisions made by informed developers across the organization. You now understand the 5 dimensions, MCDA, and the real versus illusory tension distinction. In Part 2, we'll cover the maturity ladder, organizational ownership, and the hardest scenario questions of the course. You're in the final stretch.